All right, welcome back. The next speaker is Gretchen Matthews. Gretchen is at the Department of Mathematics at Virginia Tech, and she also has a leadership position with the Commonwealth Cyber Initiative. Looks like her talk is a nice follow-up to Narayanan's earlier talk, and it will be on CSS-T codes.
Thank you, and thank you for the opportunity to share this work here with you and for the invitation to speak. Is this too loud? Is it okay?
I think it's good for us. It always sounds too loud.
Okay, I just wanted to be sure I wasn't shouting. So I really am happy to share the work that I'm about to. And you might be wondering, like, wasn't this talk supposed to happen earlier in the day? What happened with the schedule, right? There was maybe some swapping around. But when you see the title, we'll be talking about binary CSS-T codes. And so it's a actually really good placement for this topic because the last talk introduced really most of the things that we need to know, and we can use that as a jumping off point. And so I'm talking today about characterizations of CSS-T codes over the finite field with two elements and characterizations of these codes, which we hope will be useful in solving some of the problems that Narayanan mentioned in the last talk. And so I have a team of collaborators that have worked together on this project. I should acknowledge actually that much of this team started through one of those collaborated ICERM projects. And so this is a spinoff of that earlier work. All right, so just to make sure that we're on the same page and we have in front of us the operations that we will need, because we will be giving a characterization of these CSS-T codes, and it depends on some really basic code operations. And so one thing that we'll be using here is the star product of vectors and of codes. And so the star product of two binary vectors is just the component-wise product that you would take. I feel like it's what sometimes our students want to do when you ask them to take a dot product, right? In other words, you take the two binary vectors and component-wise multiplication gives you another vector over F2 of the same length. We'll be taking products of codes, in which case we do that with all code words in the code space. So if we have two codes, C and C prime, we take the star product of C and C prime for all code words C from C and C prime from C prime, and then we take the F2 span of that space to get the star product. Now for us, we'll only care about the square, so we'll be taking just the product of a code width itself under this operation. So nice and easy. We'll also have a couple of other operations that come up. And again, just to make sure that we all view these things in the same way, we will be shortening at time codes and puncturing them as needed. So I just wanted to be clear on those definitions. And so when we shorten a code, of course, we're going to take just the code words that have a 0 in the ith coordinate, right? And then we delete it. Whereas shortening, we take all the code words and just delete the ith coordinate. We might do this with collections of indices rather than single symbols or single coordinates. And so we'll use the notation shown here for that, a C sub S or a C to the S, depending on if we're shortening or puncturing with respect to a set of indices S. Another handy object for us will be the hull of a code. And so the hull of a code, of course, is just the intersection of the code and its dual. And so hulls have been studied for quite some time. I think they're a natural object, of course, in coding theory, but I think the first paper probably that featured the word hull is probably by Asmus and Key in the early 90s. More recently, hulls have become popular in the study of LCD codes, like looking for a code whose intersection with its dual is just 0. So we'll look at hulls. For us, what's going to be important are these relative hulls. And so if I have two codes of the same length, and all day today we're going to be binary, if I have two codes of the same length, then the relative hull of one code with respect to the other is just the intersection of one code with the dual of the other code. So that'll be a relative hull. So as I said, the hulls have proven useful in LCD codes. Also, the challenges that we sometimes see in trying to construct codes that have hulls of particular dimensions. This has a role in defining quantum codes that are entanglement assisted. And so that's another place where we see the hulls show up, and the relative hull as well. I don't think in this, for those of you that are returning from the last talk, I don't know that we need to go through the CSS construction again, but just to say that we will be looking at pairs of codes C1 and C2, so that C1 contains C2, and we'll be using the famous CSS construction to determine a quantum code from those two codes. And of course, we'll be interested in when such a pairing of codes is CSS-T. We learned in the last talk that CSS-T codes were defined not that long ago, actually. And this is, I believe, the definition that was given there in the literature. We saw it in the last talk as well. We can just take a look now. So we start with two codes, C1 and C2, and we'll always talk about a pair of codes so that C1 contains C2. In order to have a CSS-T code, we need the code C2 to be even, meaning all of its code words have even weight. And then this other condition, so the first condition, an even code, that's something that's quite easy to digest just upon first read. This one takes a little bit more getting used to, I think. But it just says that in order to satisfy this condition, we need for every code word of the smaller code to find within the larger, the dual of the larger code, a subcode that happens to be self-dual. And so supported on what? Well, I'm getting ahead of myself, but supported on the code word that we identified here. So these two conditions together make a CSS-T code. And this one is the one that I think gives us, more, we have to think more about that. Like if you ask someone on the street to, tell you a code, actually, we should have played this game, right? It's the last talk of the day. We should have played this game where like, can you give me a code that satisfies these conditions? And there's kind of a lot to think about, right? So it might not be easy for us to just, come up with one on the spot, right? And actually that's really what this talk is about, is how can we replace this condition with an equivalent one, of course, that is easier for us to digest, right? It'll be an equivalent characterization, so it won't be, anything new, but it will make us maybe feel a little bit more comfortable with this definition, and hopefully serve as a platform for people to actually find some of these codes. And we have some results that I'll share with you on finding codes using our characterization. All right, so again, some of this is a little bit repetitive from the last talk, but that's okay. So there is some prior additional work. This isn't meant to be comprehensive, but we have two papers that actually appeared on the archive just in the last year. So I think the first paper here was started I'm not sure when it started, a couple of years ago, maybe. It's on the archive now in May. There they study Reed-Muller codes and CSS-T codes coming from the Reed-Muller codes. They note that, it's a challenge to get asymptotically good codes, and there's this trade-off between codes with good distance and codes with high rate. So, and then more recently, there's work on query CSS-T codes. And so we'll just focus on Q equals 2. And so we'll stick to the standard definition that we saw earlier. But I do want to bring your attention to this paper, which starts to explore what would these conditions that we just saw, what would be the equivalent ones if we were going to look at codes over FQ, where Q is some power of a prime, and we're looking at codes over that field. All right. So this is what I would like to share with you. And again, in hopes that you will find it useful, as we have, but we need more ideas, of course, about how one could apply these ideas. So this is our characterization. So we'll start with two codes, C1 and C2, both binary. These form a CSS-T pair if the code generated by the dual of one code and its square lives inside the dual of C2. Okay, you might be disappointed. Do you remember I said I was going to tell you something that you would be more comfortable with and you would think that's a really nice thing to think about? Maybe this one is a little bit easier. C2 is contained in the intersection of C1 and the dual of the square of C2. This condition right here says that C2 is in the relative hull of C1 and its square. Okay, so this condition right here feels quite actionable and hopefully can help us see what are some good CSS-T codes. I'm not going to give any proofs in this talk, but we do have a paper that contains all the details, and so I'll refer you to that to see these equivalent conditions. So I want us to think about this one. I'm looking for a pair of codes C1 and C2 so that C1 contains C2 and what? C2 is contained in the relative hull of C1 and its square. as a corollary, we get that such a pair, a CSS-T pair, has the property that C2 is self-orthogonal, and the distances compare in this way. When I say the distances, these two distances are the ones that show up in the CSS construction that give rise to the lower bound on the minimum distance of the quantum code. And so what that means is if we have a CSS-T code coming from such a pair, then the minimum distance is bounded below by the minimum distance of the dual of C2. All right, so what can we do with this? Well, one thing we can do with this is we can actually propagate the CSS-T codes to some extent. And I tried to keep the slides like kind of nice and user-friendly, not lots of pictures or anything, but just to try to keep the text simple. And so with that in mind, this propagation rule, you can only do this, of course, when one of the codes isn't too big. What I mean by that is, and we'll see a definition of maximality in just a moment, but there is a slight restriction here. If C1 is already as big as it can be, then we can't propagate and get something bigger, right? But I didn't write that down. All right, so suppose we have a CSS-T pair and some vector, binary vector y, then we can get a new CSS-T pair by increasing C1 by taking the smallest code that contains both C1 and y. So we've made the bigger code bigger. This will be a CSS-T pair if and only if the product of C1 with y and, well, the code generated by that and y is what in the dual of C2. Okay. So this is nice because it allows you to increase the dimension of the code by 1. If we think back to the CSS construction, the dimension of the code that we'll get, the k value, if you will, comes from what? The difference in the dimensions of C1 and C2. So if we've increased the code in the first coordinate, then we've been able to increase the dimension by 1. An actionable condition is given here. So if I'm wondering if I have a CSS-T pair, maybe I should go back here. If I have a CSS-T pair to start with, okay, and I'm wondering if I can increase the larger code at all, then I have a source of where to find those potential vectors. I'll look in the dual of C2 and its intersection with the dual of this other code, right? So again, not so pretty, but it gives you a place to find the vectors that you can add on to actually grow your code. And so putting that together, we have this proposition that shows actually, if we start with a CSS-T pair, then, well, there's some conditions here. But the idea is that if C1 is not as big as it could possibly be already, then I can find such a y and I can grow it so that I get a higher dimensional code, quantum code.
So that preserves the distance, though.
And if the code, yes, thank you for pointing that out. If the code is non-degenerate to begin with, then yes, the distance is preserved. We need that condition. Yes.
So then that's going to stop you at some point because you clearly can't keep increasing the size of the code and just keep the distance.
Yeah. So we're going to run into problems with this source of vectors. And so it's really this idea, this lemma that kind of motivated us to look at a poset of such codes, right? Because we felt like there were going to be some barriers to increasing this, and we wanted to understand what that poset would look like. Yes.
Can you repeat what it means to be non-degenerate? Perhaps I missed this.
Yeah, so I'm sorry, I didn't define that. So here by non-degenerate, I'm just going to think about, I don't have any coordinates. I mean, there's various ways I can think about it. Probably the simplest here, since we haven't really developed any terminology, would be to just think about, I don't have any coordinates that are simultaneously 0.
Yeah.
All right. So thinking about this, moving towards this poset, if we have a CSS-T pair and we have some other pair, we're wondering if it's CSS-T as well, then, well, if I can pair these two, the component codes of these two pairs, then I will have another CSS-T pair if I satisfy this condition right here. There's kind of this natural embedding of codes that's useful. So this led us to define this partial order on the set of CSS-T pairs. And and of course, the natural way, just like one would compare, any two pairs, or we would be tempted to, we'll say that a pair C1, C2 is less than or equal to, in the partial order, C1 prime, C2 prime, if we have this containment for both C1 and C2. And then, of course, a code will be maximal with respect to one of the coordinates, like C1, for instance, if this condition is satisfied for C1, and maximal with respect to C2 equivalently. Or similarly, I should say. All right, so I'm throwing lots of like notation at you, but it's all like the components I think are quite basic, but let me show you what we can do with that. If we have a CSS-T pair C1, C2, we might wonder, like, is this as big as it could be? And what do we mean by big, right? Because we have two codes involved. We have the distance of the quantum code will depend on the dual of C2, right? And so we can ask, so there's various things that we might want to maximize, right? It might be that minimum distance, or it might be the dimension of the code. And so what we would like to think about is, how can we grow such a pair as much as possible? And so the first result along these lines I wanted to share is that such a pair will be maximal with respect to C2, meaning I can't increase C2, provided C2 is the relative Hall of C1 with respect to C1 squared. So what this means is I can look inside this Hall, right? If I can compute the Hall, then I have now found the maximal with respect to C2 pair that has C1 as a component. And similarly, if we're looking instead to increase the dimension, let's say, so we want to grow C1, then we should do so by having a code. This one's a little bit trickier, this condition, but we can find C1 in such a way, right? So, and then of course, if we want the pair to be maximal with respect to both components simultaneously, then we could define C1 and C2 so that they're related in this way. Of these conditions, this one I think is the one that feels like the greatest source of, I don't know if you call it fun, entertainment, challenge, but it's quite helpful in terms of trying to find these CSS-T codes. So the paper that was mentioned earlier that showed up on the archive this year with Bolkema and others, they studied Reed-Muller codes that were CSS-T, and they were looking at a pair of codes, perhaps like this code, these two codes here, C and D. And it's a natural source of examples for any of us to start with Reed-Muller codes, especially if you're someone who likes evaluation codes like I do. So even though they had already studied this, we were looking for examples, and we just wondered like what we could learn starting at this natural point. And so it turns out that if you take two Reed-Muller codes so that they satisfy the containment condition required, then well, if you have your D and your D prime that are defining these codes, so these would be D and D prime would be the bounds on the total degree of the polynomials that you would be evaluating to generate the Reed-Muller codes, then we already know what the dual is. Of course, it's easy to compute the star product, and I know people do star products for lots of different reasons these days, showing up here for a different reason perhaps. But that allows us to see that when we get another CSS-T pair, and it also allows us to see when we get a maximal CSS-T pair. So I think there were some questions from the paper that I mentioned earlier about are the codes that they found maximal, and I think with the tools that we have here, we can answer that question. So Reed-Muller codes are one source of examples where these techniques naturally apply. I'll show some tables later on with like explicit codes with explicit parameters. But for now, I wanted to move on to the other piece of this work, which is looking at cyclic codes and extended cyclic codes. And so there's a lot of notation here, but the main point is to say that if we have a cyclic code, what we do is we think about the cyclotomic sets that are defining that code, and then we can place a condition on the cyclotomic sets to see exactly when the codes are, the pair of codes is CSS-T. And so you can read this now if you like, or you can look at it in the paper. It's late in the day, don't you think? But the idea is that we have this way of, with a cyclic code, attaching to it this set of integers, mod n. I said we'd be binary all day. That's not necessarily true. These codes will be binary, but the cyclotomic sets, of course, might require some other value n. So you can see the setup here. We start with a field extension, though. And again, I said we were going to be binary, but we actually here start with this field extension. So we take a degree S extension, and we use it to define a cyclic code by taking a generator polynomial G that satisfies this divisibility property here. And when we do that, well, it'll give rise to this defining set J, which again is a set of integers mod n, and it'll have a sort of partner set I. So you can think about the relationships that J and I must satisfy and what G has to look like. And then what does this have to do with getting the CSS-T pairs that we were talking about? Well, we can use this point of view to consider the cyclic code as an evaluation code. And when we do this, we take a set of monomials, right? And then we look at the evaluation code that comes from this set of monomials. When we do that, we get a code here that's actually over the extension. But in this last step, we'll actually take the restriction down to the subfield, so we end up with a binary code. And lots of details, but the main point is that you can, from all this machinery, you can actually determine when such a code is CSS-T. So it gives you a way to manufacture cyclic CSS-T codes. Of course, given the cyclotomic cosets being related in such a way, as shown here in 1 and 2. So this gives us a way to define a quantum code that's CSS-T with the parameters that you see here. All right, so now there are examples. And so it wouldn't be much fun if the end of the story was we have these conditions and we can't do anything with them. So we do have some new examples, I think, coming from this perspective. Here are some Reed-Muller examples. So these here come from the characterization that we saw early on. And then tweaking some parameters allows us to get slightly better codes, as we see here. And these are all CSS-T codes. And then if we look at cyclic codes and extended cyclic codes, then we can produce additional examples using the cyclotomic cosets that we saw earlier. We can improve the parameters somewhat. I couldn't make these all fit all together, but the point is that we can make minor adjustments to increase the dimension or perhaps the minimum distance. And so actually, that's all I wanted to share with you today. So thank you very much.
Yeah, thank you for the great talk. Great to see all the new codes you have. So in terms of like, I believe that all these are like families of codes, right?
Yes.
So could you say more generally how K and D scale?
So these codes,
because I see a subset of those where actually a family we had in the paper. So we had a quantum Reed-Muller family where like that
Yes.
128, 21.4, the 256, the 512, 84. So they're all.
yeah. So some of this is like rediscovering, right?
What is the bigger family that I'm missing?
So these codes, I think, are the new family, perhaps. And the family, you're going to be disappointed in this answer. I'm sorry. the family of codes from like are where we manufacture these is using this theorem and looking for examples. So we don't have. I couldn't tell you, given a cyclotomic coset with these as its elements for I1, these for I2. Like, here's your CSS-T code that has the parameters in K and D that you're looking for. We don't have that yet, but I'm hoping by sharing this and this work here that maybe other people will see how to do that. Right now, we're using these conditions as a way to manufacture examples to try to give us insight as to like what are the families.
Fantastic. And another comment I just wanted to make. I mean, I didn't have time to mention it in my talk, but you proved this nice lower bound on the distance for any CSS-T, that it's lower bounded by the distance of C2 perp. Which is interesting because at least in the distillation protocol that I talked about, there's a noise model where you actually only care about, so there's two distances for a CSS code, right?
Yes.
So in that distillation protocol, the distance you care about is the C1 mod C2, not the C2 perp mod C1 perp. So what I'm saying is there's value also in constructing codes like this, which could have asymmetric distances because we really only care about one distance, at least for that protocol. So that could also be used.
Oh, thank you for pointing that out. I didn't realize that.
Thanks.
So I just want to ask, the shooting these sets I1, I2, how much effort did you guys optimize those fully, or because there's a lot of choice you could have there, right?
Right. So there's a lot of opportunity, let's say, to build on this work.
So you just found a couple that worked, and that was.
Well, okay, that's probably it's probably slightly more sophisticated than that. But I couldn't tell you like what exactly to do to narrow your choices.
Yeah.
So maybe it's the question for both, because you made an argument that T-gates are important in practice. I mean, they have some advantages. And then also this locality of service codes has some advantages. What do people now, like say physicists who are implementing these, say, well, is there a preference to have a service code, CSS-T, or?
So the general answer is, so think of it as, so this distillation procedure needs a code with certain properties for that procedure to work. That's a different code compared to the main code you have for the computation. So the main code you have, people have been using the surface code for a long time because it's nice. But I think given the recent constructions, and there was even some experimental breakthroughs in end of last year with like this neutral atoms based architecture, but they showed that they can go beyond surface codes and they can shine lasers and move qubits around and actually measure syndromes for the hypergraph product construction that Gretchen came up with. So they can do more non-local connections now. So I think everyone is excited about using these better codes in practice. So that's what you would use for the main computation, but it's not clear that you can use the same to do the distillation. So this CSS-T is all about that factory that keeps producing these states, which you will inject into your computation whenever you.
Okay, if we don't have other questions, thank you so much.